Take everything you have ever seen, every mountain range and ocean floor, every city and forest and desert, every cloud and snowflake and grain of sand, every person who has ever lived, every animal that has ever moved, every structure humanity has ever built, every skyscraper, every dam, every bridge, every satellite and space station orbiting above us right now, all of the planets in the solar system, the sun itself, a ball of gas so large that more than 1 million Earths could fit inside it. All of it, everything, compressed into a single quantity. The total amount of matter that exists, visibly and detectably, within the observable universe. Now to the observable universe itself, a sphere 93 billion light years in diameter, the largest volume of space from which light has had time to reach us since the Big Bang. Calculate its total volume. Divide the matter by the volume. The average density of matter in the observable universe is approximately 9.9 times 10 to the power of minus 30 grams. Into the equivalent number of hydrogen atoms, the lightest atom, you would get roughly 6 hydrogen atoms per cubic meter. 6 atoms in the space of an average living room. 6 atoms per room-sized volume, on average, everywhere. This is what I mean when I say the universe is empty. Not empty like a vacuum chamber. Not empty like outer space as you picture it when someone says outer space. Empty in a way that has no analogy in ordinary experience, because ordinary experience takes place entirely within extraordinary exceptions to the cosmic average. Planets are extraordinary exceptions. Solar systems are extraordinary exceptions. Even interstellar space, the cold void between stars that we usually imagine when we think about emptiness, is many orders of magnitude denser than the cosmic average. The universe is not mostly made of stars and planets with some empty space between them. The universe is mostly made of almost nothing, with a few vanishingly rare wisps of structure scattered through a void so total that the structures themselves are barely detectable against the background of nothingness. And the more precisely you look at this emptiness, the stranger it gets. Because the emptiness is not random. It is not uniformly distributed. It has a shape, a vast, intricate, three-dimensional architecture of filaments and voids and walls and nodes that looks, when visualized at the largest scales, like the inside of something biological, like foam, like neurons, like a structure that should not be there, built by nothing, out of almost nothing, over 13.8 billion years. This video is about that emptiness, where it comes from, what it contains, why its shape means what it means, and why the specific way the universe is empty is one of the most important facts about reality, carrying implications that reach from the nature of dark matter to the question of whether we are alone. Chapter 1: The Scale Problem. Why human intuition fails completely. Before we can talk about why the universe is so empty, we need to be honest about something. Human beings are constitutionally incapable of intuiting the relevant scales. This is not a metaphor or a rhetorical flourish. It is a cognitive fact with a specific cause. Every scale of distance and density that human intuition was shaped by natural selection to handle, the scale of a body, a tool, a landscape, a day's walk, is so far removed from the scales relevant to cosmic emptiness that the intuition simply does not apply. It is like trying to use a ruler to measure the temperature of the sun. The instrument was not built for the measurement. So let's build an instrument. Let's actually try to construct an intuition for what the relevant scales mean, knowing in advance that the exercise will fail, but that the failure itself instructive. Start with the Earth. The Earth has a radius of about 6,371 kilometers. Its volume is approximately 1.08 times 10 to the 12th power cubic kilometers, or about 1 trillion cubic kilometers. The density of the Earth, averaged across its iron core, its rocky mantle, its thin crust, is about 5.5 grams per cubic centimeter. That is roughly 5.5 times the density of water. The Earth, as a material object, is neither exceptionally dense nor exceptionally tenuous. It is a middling rock. Now move outward to the solar system. The Sun contains 99.86% of all the mass in the solar system. All the planets, moons, asteroids, comets, and dust together account for 0.14%. The volume of the solar system, if you define it as the sphere bounded by the heliopause, the boundary where the solar wind meets the interstellar medium at about 100 astronomical units from the Sun, is approximately 4.2 times 10 to the power of 30 cubic meters. The total mass of the solar system is approximately 2 times 10 to the power of 30 kilograms, almost all of it in the Sun. The average density of the solar system is therefore about 2 times 10 to the power of minus 10 kilograms per cubic meter, already far too low to detect without calculation. If you compressed the solar system to the density of water, it would fit inside a cube about 1,260 kilometers on a side. The solar system, the region of space we consider our home, is almost nothing. Now move outward to interstellar space. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. 1 light-year is approximately 9.46 times 10 to the power of 12 kilometers. Proxima Centauri is therefore about 40 trillion kilometers away. If the Sun were the size of a marble, a sphere 1 centimeter in diameter, then Proxima Centauri would be another marble located approximately 284 kilometers away. Imagine 2 marbles, one in London, one somewhere around Paris. Between them, nothing. No air, no dust, no anything detectable. That is the density of interstellar space in our immediate neighborhood. And our immediate neighborhood is one of the denser regions of the galaxy. The Milky Way contains somewhere between 200 and 400 billion stars. The estimate is uncertain because most stars are dim red dwarfs that are difficult to count at large distances. These 200 to 400 billion stars are distributed through a disk roughly 100,000 light-years in diameter and about 1,000 light-years thick. Though the disk has a complex structure with significant variation in thickness, the average density of stars in the Milky Way disk is roughly 0.14 stars per cubic light-year, meaning that, on average, you would need to search through a cube of space 1.9 light-years on each side to find a single star. The stars are not crowded. They are not close to each other. The night sky gives a deeply misleading impression of stellar density. We see thousands of stars, but they are distributed through an enormous volume, and most of the volume is empty. Now, move to the scale of the observable universe. The Milky Way itself, which seems vast from any human perspective, is one of roughly 2 trillion galaxies in the observable universe, according to the most comprehensive estimates from deep field surveys. 2 trillion galaxies, each containing, on average, hundreds of billions of stars. And yet, the observable universe is large enough that the average density of all this matter works out to those 6 hydrogen atoms per cubic meter. 6 atoms per cubic meter. The Milky Way is 100,000 light-years across and contains 400 billion stars, and the universe contains 2 trillion Milky Ways, and still the average density is 6 atoms per cubic meter. The volume of the universe is so incomprehensibly large that 2 trillion galaxies full of hundreds of billions of stars each barely registers as a smear of dust against the background of the void. This is the scale problem. The universe is not empty despite containing a vast amount of matter. It is empty because the volume it occupies is larger than the matter it contains by a margin that defeats any attempt at intuition. The emptiness is not the background. The emptiness is the main event. Chapter 2: What is actually out there? A taxonomy of the void. When we say the universe is mostly empty, we need to be careful about what we mean by empty, because the cosmic void is not entirely empty in the strict sense of containing nothing. It contains several things that are very strange, very tenuous, or very poorly understood. And knowing what they are is essential for understanding what the emptiness actually consists of. The first thing the void contains is ordinary matter in its lowest density form, the intergalactic medium, or IgM. The intergalactic medium is the gas, primarily hydrogen and helium, that fills the spaces between galaxies. It is extraordinarily diffuse. The average density of the IgM is roughly 10 to 100 times the cosmic mean, which puts it at about 10 to 100 hydrogen atoms per cubic meter. Most of this gas is not cold neutral hydrogen, but hot, ionized plasma, heated to temperatures of 10 to the power of 5 to 10 to the power of 7 Kelvin by the ultraviolet radiation from quasars and young star-forming galaxies, and by shock waves from the large-scale flows of gas along the cosmic web. This hot component of the IgM, called the warm-hot intergalactic medium, or WHIM, is so diffuse and so hot that it emits primarily in the soft X-ray band and has been extraordinarily difficult to observe directly. It was only in the last decade that convincing direct detections of the WHIM were made by X-ray telescopes, confirming what simulations had long predicted. The significance of the WHIM is partly a matter of bookkeeping. For decades, there was a discrepancy in the cosmic baryon budget. The total amount of ordinary matter predicted by Big Bang nucleosynthesis, the process that produced hydrogen and helium in the first minutes after the Big Bang, was larger than the amount that had been directly observed in stars, galaxies, and dense gas clouds. The missing baryons, the ordinary matter that was predicted to exist but not found, were a puzzle. The WHIM turned out to be where most of them are. Most of the ordinary matter in the universe is not in stars. It is not in planets. It is not in galaxies. It is in the tenuous, scorching hot filaments of the intergalactic medium, stretched between galaxies along the threads of the cosmic web. Think about what this means. Even among ordinary matter, the matter we can see, the matter made of protons and neutrons, the matter that makes up everything you have ever touched. The majority is not in the visible structures we call galaxies. It is in the emptiest parts of the universe, spread so thin as to be essentially invisible. The stars and galaxies, which seem to constitute the universe when we look at the night sky, are a small fraction of even the ordinary matter. They are the foam on the surface of something much larger and much emptier. The second thing the void contains is dark matter. Dark matter is the name we give to whatever is responsible for the gravitational effects that cannot be explained by the ordinary matter we can observe. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. The rotation curves of galaxies, which rotate too fast at their edges to be consistent with the visible mass. The gravitational lensing of light by galaxy clusters, which shows more mass than is visible. The formation of large-scale structure in the universe, which requires a non-baryonic component of matter to match the observed clustering of galaxies. And the CMB temperature fluctuations, which are precisely consistent with a universe containing about 27% dark matter and only 5% ordinary matter. Dark matter does not emit, absorb, or reflect light. It does not interact electromagnetically at all. It interacts only through gravity and, possibly, through the weak nuclear force. This means it is invisible, not just dim, not just hard to see, but genuinely undetectable by any instrument that works by collecting photons. We cannot image it directly. We can only infer its presence from its gravitational effects. It fills the universe not in the way that ordinary matter fills space, concentrated in dense clumps of gas and stars, but in a more diffuse, extended way, forming the massive dark matter halos that surround galaxies and galaxy clusters, and tracing the large-scale cosmic web of filaments and voids. Dark matter is everywhere, including in the void. The density of dark matter in the cosmic voids is lower than the average, but it is not zero. The voids are not simply regions where dark matter is absent. They are regions where dark matter is less concentrated than average, which is itself the result of the same gravitational dynamics that created the voids in the first place. The third thing the void contains is dark energy, or more precisely, the void contains the effects of dark energy. Dark energy is even more mysterious than dark matter. Unlike dark matter, which at least behaves gravitationally like matter, clustering in halos, having a defined density, dark energy is perfectly homogeneous. It does not cluster. It does not have a higher density in some regions than others. Its density appears to be the same everywhere, at all times, a property consistent with the cosmological constant, the simplest model of dark energy. This uniform density means that dark energy becomes increasingly dominant as the universe expands. As ordinary matter and dark matter are diluted by the growing volume of the universe, the dark energy density remains constant, and its fraction of the total energy budget grows. Today, dark energy constitutes approximately 68% of the total energy content of the universe. The fourth thing the void contains is radiation, primarily the cosmic microwave background photons that we discussed in the previous video on the cold of space. These 411 photons per cubic centimeter permeate every region of space equally, including the deepest cosmic voids. They are the thermal afterglow of the Big Bang, and they are everywhere. So, the void contains a very thin plasma of ordinary matter, an invisible scaffold of dark matter, a perfectly homogeneous field of dark energy, and a bath of ancient photons. It is not nothing, but it is so close to nothing, and what it does contain is so unlike anything in ordinary experience that empty remains the most accurate single word for it. Chapter 3: The Cosmic Web. The shape of emptiness. The emptiness of the universe is not formless. It has a structure. That structure is called the cosmic web, and it is the largest coherent structure in existence. A three-dimensional network of filaments, walls, nodes, and voids that extends through the entire observable universe and organizes every galaxy and galaxy cluster into a pattern that, when seen at large scales, resembles nothing so much as a luminous foam. The cosmic web was first theoretically predicted in the 1970s and early 1980s through N-body simulations, computer simulations of the gravitational interactions of large numbers of particles representing dark matter. The simulations showed that if the universe started with small random density fluctuations, the kind predicted by inflation and confirmed by the CMB, gravity would amplify those fluctuations over time in a specific way. Matter would flow away from underdense regions and toward overdense regions, creating a network of dense filaments and sheets with vast empty voids between them. The pattern that emerged from the simulations, long before it was confirmed by observation, was a cosmic web. The observational confirmation came with the first large-scale galaxy redshift surveys. The first clear detection of the large-scale structure of the cosmic web came from the CFA redshift survey in the 1980s, which revealed the Great Wall, a sheet of galaxies stretching over 500 million light-years. But the full three-dimensional map of the cosmic web at large scales only became possible with the Sloan Digital Sky Survey, SDSS, which began operations in 2000 and has mapped the positions of hundreds of millions of galaxies across a significant fraction of the observable universe. The SDSS map of the universe, when you look at a thin slice through it, shows the cosmic web with breathtaking clarity, a network of bright filaments and sheets of galaxies surrounding and defining enormous spherical regions that are almost completely empty. Those empty regions are the cosmic voids. They are the dominant structural feature of the universe by volume. Voids are underdense regions where the matter density is significantly below the cosmic average. That formed because matter flowed away from them under gravity toward the surrounding filaments and walls. The typical cosmic void has a diameter of 10 to 100 million light-years, though the distribution is broad and some voids are significantly larger. The void interiors are not quite empty. They contain some tenuous gas and dark matter, and occasionally a small, isolated galaxy or two. But their density is typically 20 to 30% of the cosmic average. They are among the emptiest large-scale regions in the observable universe. By volume, voids occupy approximately 70 to 80% of the total volume of the observable universe. 70 to 80% of the universe's volume is in these nearly empty spherical regions, with the matter of the cosmos, the filaments, walls, clusters, and superclusters concentrated into the remaining 20 to 30% of volume. But within that 20 to 30%, the matter is still distributed unevenly. The filaments themselves are thin compared to the spaces between them, and within the filaments, galaxies are separated by millions of light-years of intergalactic space. The void fractions at every scale of structure are high, The universe is empty at the level of galaxies, within clusters, clusters within superclusters, superclusters within the large-scale structure, and the large-scale structure within the total volume. Emptiness is fractal in character. Every level of zoom reveals more emptiness than matter. The geometry of the cosmic web has three main structural elements. The nodes, the densest points where multiple filaments intersect, are galaxy clusters and superclusters. These are the most massive gravitationally bound objects in the universe. The largest known supercluster, the Hercules Corona Borealis Great Wall, spans approximately 10 billion light-years and contains an astonishing concentration of matter relative to the cosmic average. But it is still predominantly empty space, just less empty than the voids. The filaments connecting the nodes are the highways of the cosmic web, ribbons of gas and dark matter along which galaxies are strung like beads on a wire, stretching for hundreds of millions of light-years. Between the filaments are the walls, flattened sheets of matter that form the two-dimensional boundaries of voids. And inside the boundaries formed by the walls, filaments, and nodes are the voids themselves, spherical or ellipsoidal regions of near emptiness, growing slightly larger as the universe expands, and matter continues to drain away from them toward the surrounding structure. What created this specific architecture? The seeds of the cosmic web were laid in the first fraction of a second after the Big Bang, during inflation. The period of exponential expansion that stretched quantum-scale density fluctuations to macroscopic sizes. These fluctuations were the density variations that show up as temperature variations in the CMB at the level of 1 part in 100,000. They are the fundamental input, the tiny initial differences in density from which everything, every galaxy, every void, every filament was eventually shaped by gravity. The process by which these tiny fluctuations grew into the cosmic web we observe today is called gravitational instability, and it is one of the most important physical processes in cosmology. The mathematics of gravitational instability describes how a small overdensity, a region with slightly more matter than average, generates a slight excess gravitational pull on the matter around it. This extra pull causes matter to flow slowly toward the overdensity, increasing its density, increasing its gravitational pull, attracting more matter, and so on in a positive feedback loop. Meanwhile, the underdense regions become increasingly empty as their matter flows away. The process is self-amplifying and, given enough time, turns a smooth distribution with 1 in 100,000 variations into the dramatic contrast of the cosmic web, with dense clusters at the nodes and nearly empty voids between them. The same physics that makes sand dunes form in a wind or snowflakes accumulate in corners operates at the scale of billions of light-years to organize the universe into filaments and voids. Dark matter is essential to this process. Without dark matter, the density fluctuations in ordinary matter at the time of recombination would have been too small to grow into the structures we observe within the age of the universe. Ordinary matter was tightly coupled to the photon-baryon plasma until recombination, which prevented its density fluctuations from growing. Dark matter, which does not interact with radiation, began forming overdensities, dark matter halos, much earlier, before recombination. By the time ordinary matter was free to move, the dark matter halos were already there, providing gravitational wells into which the ordinary matter could fall. Dark matter built the scaffolding of the cosmic web, and ordinary matter fell in along the pre-existing dark matter structure. The filaments and walls and nodes we observe are, at their core, dark matter structures. The galaxies are luminous markers of the dark matter architecture, not the architecture itself. Chapter 4. The supervoids, the emptiest places in the universe. Within the cosmic web, not all voids are equal. The typical void, 10 to 100 million light-years in diameter, about 20 to 30% of the cosmic mean density, is already extraordinary by human standards. But there is a class of structures that dwarf even the typical cosmic void, the supervoids. These are underdense regions of exceptional size and exceptional depth, and they are among the most alien environments the universe contains. The largest confirmed supervoid in the observable universe is the KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who published evidence for its existence in 2013. The KBC void is approximately 2 billion light-years in diameter, roughly 20 times the size of a typical cosmic void, and it is centered roughly on our own position. The Milky Way, the local group, and the broader region of the universe within a few 100 million light-years of us appears to be inside this supervoid. The KBC void is a local underdensity. The density of matter within it is approximately 20% below the cosmic mean. This is not a region of total emptiness. Galaxies exist within it, including the Milky Way. But it is a region where the average density of matter is measurably lower than the cosmic background. The existence of this local void has attracted significant attention because it may be relevant to one of the most contentious current debates in cosmology, the Hubble tension. The Hubble tension is the discrepancy between two independent measurements of the Hubble constant, the parameter that describes the current rate of expansion of the universe. Measurements of the Hubble constant derived from the CMB, the early universe, method give a value of approximately 67.4 kilometers per second per megaparsec. Measurements derived from the local universe using Type 1a supernovae and the cosmic distance ladder consistently give a higher value, approximately 73 kilometers per second per megaparsec. The discrepancy between these two values is about 9% and is now significant at the level of 4 to 5 sigma, well beyond what can be explained by measurement error. One proposed explanation involves the KBC void. If we are inside a large local underdensity, the local expansion rate of the universe could be enhanced relative to the global average, because matter flows outward from voids since there is less gravitational pull inside them, which could make the local expansion appear faster than the global expansion. This would reconcile the higher local Hubble constant with the lower global value. The KBC void explanation for the Hubble tension is debated, and not all analyses of the local density field support it, but it remains one of the more physically motivated proposals on the table. A different supervoid, one that does not contain us, made headlines for a different reason. The SDSS Great Cold Spot, sometimes called simply the CMB Cold Spot Supervoid, is a large underdensity at a distance of approximately 1.8 to 3 billion light-years from Earth, in the direction of the constellation Eridanus. This region has been studied in the context of the CMB cold spot. the anomalously cold region in the cosmic microwave background that was mentioned in the cold space script. The proposed connection is the integrated Sachs-Wolf effect. Photons of the CMB crossing a void lose energy because the gravitational potential well they enter is not as deep when they exit as when they entered, due to the void growing shallower from cosmic expansion driven by dark energy. A large enough supervoid in the right direction could therefore produce a cold spot in the CMB, and there appears to be a supervoid in approximately the right location. The supervoid associated with the CMB cold spot is estimated to be approximately 300 to 1,800 million light-years in diameter, depending on the analysis. The wide range reflects genuine uncertainty in the observations. If the larger estimates are correct, it is one of the largest underdense structures ever identified, and it could account for a significant fraction of the CMB cold spot's temperature deficit. The analysis has been updated multiple times as better galaxy survey data became available, and the most recent comprehensive studies find evidence for a supervoid consistent with the cold spot location, though the quantitative match between the supervoid's properties and the full temperature deficit remains uncertain. Beyond these specific examples, supervoids are a general feature of the large-scale structure of the universe. The statistical distribution of void sizes and depths is a sensitive probe of cosmological parameters, particularly dark energy and the growth rate of structure. A universe with more dark energy expands faster, which empties the voids more effectively, because matter flows out faster, and also makes the voids larger. Measuring the statistical properties of voids across cosmic time, watching how voids grow and deepen as the universe evolves, is a powerful way to test models of dark energy and the growth of structure. Surveys like the Dark Energy Survey, DES, and the upcoming Euclid satellite have been designed in part to use voids as cosmological probes in exactly this way. There is something philosophically striking about the largest voids. A sphere 2 billion light-years in diameter contains almost nothing, fewer galaxies than you would expect from the cosmic average, spread through a volume so large that you could spend the entire history of the universe flying through it at the speed of light and not exit the other side. These are regions of space that have been essentially abandoned by matter. Everything gravitationally interesting flowed away from them over billions of years toward the surrounding filaments and walls. What remains is a near emptiness of extraordinary purity, the universe's own approximation of nothing. Chapter 5. Why is there so much nothing? The origin of cosmic emptiness. The cosmic web exists. The voids are real. The question that remains is the deepest one. Why? Why is the universe structured this way? Why is it mostly empty, with matter concentrated in a thin web of filaments and walls, rather than distributed uniformly, or concentrated in some completely different pattern? The short answer is because of the specific character of the density fluctuations that inflation produced, combined with the specific properties of dark matter, combined with the effects of dark energy, combined with 13.8 billion years of gravitational dynamics. The long answer is one of the most beautiful stories in all of physics. Let's start with inflation. The inflationary epoch, the period of exponential expansion in the first 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the Big Bang. is the mechanism that is currently thought to have generated the initial density fluctuations that seeded all subsequent structure. During inflation, the universe expanded by a factor of at least 10 to the 26th power, possibly much more, in an extraordinarily short time. Any quantum fluctuation in the inflaton field, the hypothetical field driving inflation, was expanded to macroscopic size. These quantum fluctuations became the seeds of cosmic structure. Microscopic quantum noise, stretched to the scale of the observable universe, froze into classical density perturbations that persisted after inflation ended and the universe transitioned to the hot Big Bang. The critical property of the density fluctuations that inflation produces is that they are very nearly scale invariant. Scale invariant means that the amplitude of density fluctuations is approximately the same on all scales. Large and small perturbations are of similar magnitude. This is called the Harrison-Zeldovich spectrum, and it has a specific mathematical form, a power spectrum with spectral index approximately equal to 1, that has been confirmed by CMB measurements to extraordinary precision. The Planck satellite measured the spectral index to be 0.9649, plus or minus 0.0042, very close to 1, as predicted, but measurably different from 1 in a way that constrains the details of the inflationary model. The near-scale invariance of the initial perturbations means that the universe started with fluctuations at every scale, not preferentially at any particular scale. What determined the specific architecture of the cosmic web, the particular scales at which structures formed, the specific sizes of voids and filaments, was not the initial fluctuations themselves, but the subsequent evolution of those fluctuations under gravity, modulated by the properties of dark matter and the expansion of the universe. Dark matter plays the central role here. The dominant component of dark matter is thought to be cold dark matter, CDM, where cold means that the dark matter particles were moving non-relativistically when they decoupled from the primordial plasma. Cold dark matter behaves differently from hot dark matter, which would be fast-moving particles like neutrinos, in a crucial way. It can form structures at small scales. Hot dark matter, because it moves fast, streams freely out of small overdensities before they can gravitationally collapse, a process called free streaming. Hot dark matter would erase the small-scale structure, producing a universe where large-scale structures form first and small-scale structures form later by fragmentation. Cold dark matter does not stream away from small overdensities, so small-scale structures form first and larger structures form later by hierarchical merging. This is the hierarchical structure formation scenario. The hierarchical scenario makes a specific prediction. Small dark matter halos form first, then merge to form progressively larger halos. The first dark matter halos formed were tiny, far smaller than any galaxy, and they merged over cosmic time to form the halos hosting dwarf galaxies, then galaxy groups, then galaxy clusters, then superclusters. The largest structures in the universe, the nodes of the cosmic web, are still forming today. This hierarchical, bottom-up assembly of structure is confirmed by observations. Distant galaxies, which we observe as they were when the universe was young, are smaller, less massive, and less structured than nearby galaxies, exactly as expected if they have been growing by hierarchical merging over cosmic time. The voids form in the opposite process. As overdensities grow by accreting matter from their surroundings, the underdense regions between them lose matter. The density in the underdense regions decreases below the cosmic mean, creating underdense voids. Matter flowing out of voids along the dark matter filaments contributes to the growth of the overdensities. The voids grow not just because matter leaves them, but because the universe continues to expand, stretching the voids larger over time. Dark energy contributes to this. The accelerating expansion driven by dark energy makes the voids expand faster than they would in a matter-dominated universe, deepens the underdensity within them, because less matter has time to flow in from outside before the expansion stretches everything apart, and stabilizes the cosmic web against further collapse at the largest scales. The interplay between gravitational collapse and cosmic expansion is what determines the specific geometry of the cosmic web. In a universe with no dark energy, one that would eventually recollapse in a big crunch, the voids would empty out, but eventually the filaments and walls would collapse into each other, and the cosmic web would give way to a dense, uniform plasma. In our actual universe, dark energy prevents this eventual collapse. The current cosmic web, the filaments, voids, clusters, and superclusters, is not a transient intermediate stage on the way to something denser. It is the final state. The structures that exist now will not merge further at the largest scales. Dark energy is accelerating the expansion, and the largest structures will eventually be torn apart by the expansion rather than collapsing further. The cosmic web we observe today is the end point of structure formation, not a step along the way. This means that the emptiness of the universe is, in a deep sense, permanent. The voids will grow larger as the universe expands. The filaments will thin as matter within them is consumed by the galaxy clusters at their nodes, and as the expansion stretches them. Individual galaxy clusters may collapse further, building ever larger gravitationally bound objects, but the large-scale architecture, the foam of voids and filaments, will remain and grow increasingly empty until, in the far future, the individual galaxy clusters themselves are isolated, separated by expanding voids so vast that light from one cluster can never reach another. Chapter 6: The Fermi Paradox and the Empty Universe. Are we alone? The cosmic web is empty. The universe is mostly void, and scattered through that void are 2 trillion galaxies, each containing hundreds of billions of stars, each star a potential host of planets, each planet a potential host of chemistry, some of those chemistry experiments running for billions of years. The question of whether life exists elsewhere in this vast, nearly empty cosmos is one of the oldest questions in science, and the emptiness itself is deeply relevant to the answer. The Fermi Paradox, posed informally by physicist Enrico Fermi in 1950 and formalized by Michael Hart in 1975, is the observation that the universe appears old enough and large enough to have produced technological civilizations long before ours, civilizations that should have had time to spread through the galaxy and make their presence known, and yet we see no evidence of them. Where is everybody? The paradox has many proposed resolutions, and most of them are relevant to the structure of the universe in one way or another. But one resolution that rarely receives enough attention is this: perhaps the universe's emptiness itself is the answer. Consider the geometry of the cosmic web. The 2 trillion galaxies of the observable universe are not uniformly distributed. They are concentrated in filaments and walls, with enormous voids between them. The average separation between galaxies is millions of light years. Even within a galaxy, stars are separated by light years, and the vast majority of those stars are in the cold, dim outer reaches of the galactic disk, where stellar encounters are so rare as to be irrelevant on human timescales. The sheer scale of even interstellar distance, let alone intergalactic distance, means that without faster-than-light travel, which current physics forbids, or extremely long-lived civilizations prepared to wait millions of years for signals and responses, the universe is effectively partitioned into isolated cells, each containing one galaxy or perhaps one gravitationally bound group of galaxies, separated from all others by an impassable expanse of void. The cosmic event horizon, the boundary beyond which the accelerating expansion of the universe means that light can never reach us, currently sits at approximately 16 billion light years. Galaxies beyond this horizon are permanently unreachable. Even signals sent today from a civilization in a galaxy near the cosmic horizon would never arrive. The expansion of the universe is literally preventing communication between the most distant parts of the cosmos. The emptiness is not merely a matter of there being nothing between galaxies. It is a matter of the expansion of the universe, making the emptiness effectively infinite for practical communication purposes. But even within a single galaxy, the distances are formidable. The Milky Way is 100,000 light-years in diameter. A radio signal from Earth, traveling at the speed of light, has so far reached only about 100 light-years. A sphere containing perhaps a few hundred stars, less than a millionth of the galaxy's total stellar population. The vast majority of the galaxy has not yet heard from us. In the 4.5 billion years that Earth has existed, the electromagnetic signal of any life on Earth has reached only the tiniest fraction of the galaxy. The galaxy is so large, and life has existed on Earth for so short a fraction of the galaxy's history, that there simply has not been enough time for any signal to propagate to most stars and return, even if there were civilizations to receive them. This is a version of the Fermi paradox's solution, known as the rarity of interstellar communication. The universe is so vast and signals travel so slowly that even a galaxy full of civilizations might be essentially incommunicado with each other. This is not a satisfying resolution to the paradox. It does not explain why we do not observe the infrared signatures of Dyson spheres or the directed energy of starship propulsion systems, but it is a constraint. The emptiness of the universe imposes a minimum isolation on any civilization in it. You are alone in your corner of the cosmos, not necessarily because there is no one else, but because the universe is too large for the news of anyone else's existence to have reached you yet. There is a related but distinct argument that the emptiness of the universe might be evidence against abundant technological life, not just a barrier to communication, but a physical constraint on expansion. The great silence is not just the silence of empty space. It is the silence of empty cosmic space that should, by now, show some sign of engineering. If civilizations emerged frequently and then spread through their galaxies even at a fraction of the speed of light, the galaxy would have been colonized long ago. The fact that it has not been, the fact that no clear sign of galactic engineering exists, is the Fermi paradox proper. One of the most interesting structural aspects of this argument involves the cosmic web. If civilizations are rare, if technological life exists in only a tiny fraction of galaxies, separated by the enormous voids of the intergalactic medium, then the probability that any two such civilizations are close enough to communicate is extraordinarily low. Each civilization is isolated by the geometry of the web, surrounded by empty void in all directions, with the nearest galactic neighbor millions of light years away, and any civilization in that neighbor separated from ours by millions of years of light speed travel time. Even a flourishing intergalactic community of civilizations, each aware of the others, would take millions to billions of years to exchange a single message and receive a reply. The cosmic web is not just a structure of matter, it is a structure of isolation. Chapter 7: The Void Galaxies. Life at the emptiest address in the universe. Not everything in the cosmic web follows the pattern of dense nodes and thin filaments. Within the great voids, isolated from the galaxy clusters and filament-spanning sheets of the web's main structure, there are galaxies. Small, peculiar, lonely, and scientifically fascinating. These are the void galaxies, and they represent one of the strangest evolutionary environments in the universe. Void galaxies are galaxies that reside in the interior of large cosmic voids, far from any filament or wall. They are typically small. Dwarf ellipticals and dwarf irregulars are the most common types found in voids, and they are genuinely isolated. Their nearest neighbors are often tens of millions of light years away. They have evolved without the gravitational interactions, mergers, ram pressure stripping, and environmental quenching that shape the properties of galaxies in dense environments like clusters and groups. They are cosmological hermits. The study of void galaxies is a direct experiment in cosmic isolation. By comparing their properties to galaxies in dense environments, astronomers can isolate the effects of environment on galaxy evolution. And the results have been striking. Void galaxies are bluer and have higher star formation rates than their counterparts in dense environments. They have more gas, the raw material for star formation, because they have not undergone the processes that strip gas from galaxies in clusters, such as ram pressure stripping from the intracluster medium. They are younger in the sense of their stellar populations, because they have been forming stars continuously rather than having their star formation quenched by environmental effects. In a sense, void galaxies are what galaxies look like when they are left alone, when the complicated environmental processes of dense cosmic environments are removed. They are simpler, in some ways more primitive, and they offer a window into the baseline evolutionary trajectory of a galaxy unperturbed by its neighbors. The void is not merely an absence of structure, it is an environment with its own evolutionary consequences, and the galaxies that inhabit it carry the signatures of their lonely location in their star formation histories, gas contents, and morphologies. There is something almost poignant about the void galaxy. A small island of stars and gas floating in the near emptiness of a cosmic void, millions of light years from its nearest neighbor, evolving in isolation over billions of years. If any of those stars have planets, and if any of those planets have life, the inhabitants would look out at a sky even emptier than ours. The nearest galaxy would be a faint smudge, barely detectable without technology. The cosmic web's nearest filament might be hundreds of millions of light years away. The universe, from the surface of a void galaxy's planet, would look truly, almost perfectly empty. A vast darkness with a tiny island of light at its center and almost nothing else anywhere in any direction. This is, of course, a version of what we already experience. The Milky Way is not a void galaxy. It sits in a modest overdensity, the Local Group, which is part of the Virgo supercluster and the broader Laniakea supercluster. But the night sky, as seen from Earth, is already dominated by darkness. Even in a galaxy with hundreds of billions of stars, even in a supercluster with thousands of galaxies, the sky is almost entirely black. The structures that seem vast from inside them, the Milky Way, the Local Group, Laniakea, are themselves barely detectable smudges in the context of the full cosmos. The void galaxy simply takes this to an extreme. It is a reminder that the cosmic web's emptiness is not an abstraction computed from statistical surveys. It is a physical environment experienced, if anyone is there to experience it, as an almost complete isolation in a universe that seems, from that vantage point, to contain nothing but one small island of stars and the immensity of the dark. Chapter 8. The observable universe versus the real universe. What lies beyond everything we have discussed so far? The cosmic web, the supervoids, the 2 trillion galaxies, the 6 atoms per cubic meter, refers to the observable universe. The observable universe is not the universe. It is the portion of the universe from which light has had time to reach us since the Big Bang. It is defined by a horizon, the distance that light, traveling at 300,000 kilometers per second, since the moment of the Big Bang 13.8 billion years ago, has been able to cross. That horizon gives us the observable sphere, 46.5 billion light-years in radius, 93 billion light-years in diameter, and everything within it is, in principle, accessible to our instruments. Everything outside it is not. And here is the thing. There is almost certainly an enormous amount outside it. How enormous? The answer depends on what happened during inflation, and the honest answer is that we do not know with precision, but we can make some estimates. The inflationary epoch expanded the universe by a factor of at least 10 to the power of 26 in a tiny fraction of a second. Before inflation, the region that would become our entire observable universe was smaller than a subatomic particle. After inflation, it was expanded to macroscopic size, and the universe as a whole, the full extent of everything that exists, not just the part we can see, was expanded to a size that dwarfs our observable sphere by an almost incomprehensible factor. The minimum size of the total universe, based on current observational constraints on its geometry, is at least 250 times larger than the observable universe in radius, meaning its volume is at least 250 cubed times larger, or more than 15 million times the volume of what we can see. But this is a lower bound derived from the flatness of the universe's geometry. If inflation lasted longer than the minimum required, the total universe could be vastly larger, perhaps 10 to the 23rd power, times the volume of the observable universe, perhaps more. Some inflationary models imply a universe essentially infinite in extent, with the observable portion being an infinitesimally small sample of the whole. If the universe extends far beyond our observable horizon, then everything we have described, the 2 trillion galaxies, the cosmic web, the supervoids, is just our local neighborhood in a vastly larger structure. The same processes that created the cosmic web here would operate throughout the broader universe. The same density fluctuations from inflation, the same dark matter dynamics, the same dark energy-driven expansion. There would be more cosmic webs, more voids, more galaxies, more supervoids, essentially the same architecture, repeated across a volume so large that it makes our observable universe look like a single grain of sand on an infinite beach. The question of whether the universe is truly infinite or merely very, very large but finite is one of the most profound open questions in cosmology. An infinite universe has specific implications. An infinite universe with a finite density of matter contains an infinite amount of matter. An infinite universe with a finite density of galaxies contains an infinite number of galaxies. And if the number of galaxies is infinite, and each galaxy contains a finite number of stars, and each star has a finite chance of hosting planets with life, then by the mathematics of infinity, every possible configuration of matter that can exist will exist somewhere, infinitely many times, including a planet identical to Earth, including a person identical to you right now, reading these words. This is not science fiction. It is a straightforward implication of standard inflationary cosmology combined with an infinite universe, and it is taken seriously as a theoretical possibility by a significant number of cosmologists. The physicist Max Tegmark has written extensively about this scenario, the Level 1 multiverse, and argued that it is an unavoidable prediction of inflation in a flat, infinite universe. The nearest duplicate of Earth in this scenario would be approximately 10 to the power of 10 to the power of 29 meters away, a number so large that writing it out in decimal notation would require more digits than there are atoms in the observable universe. So far away as to be forever beyond any observational reach. But there, in principle, nevertheless. What makes this idea scientifically uncomfortable is not that it is obviously wrong, but that it is essentially untestable. No observation from within our observable bubble can confirm or deny the existence of a Level 1 multiverse, because by construction, the rest of the universe is causally disconnected from us. Anything beyond the observable horizon has had no influence on the physics we measure here, and we have had no influence on it. It might as well not exist from an empirical standpoint. And yet the mathematics of inflation, which is our best current model of the early universe, and which is supported by the CMB data in multiple ways, strongly implies that something exists beyond the horizon. The disagreement is not about whether the universe is larger than our observable bubble. It almost certainly is. The disagreement is about how much larger and whether the extra size is infinite or merely enormous. This is one of those questions at the frontier of science where mathematical reasoning has outrun observational access. And it is genuinely unclear whether the question is one that physics can ever answer, or whether it belongs permanently in the domain of metaphysics. The boundary between the two is one of the most interesting fault lines in modern cosmology, and the emptiness beyond our horizon sits squarely on it. The emptiness beyond our observable horizon is the ultimate emptiness, not the 70 to 80% void fraction of the cosmic web, but the total unknowability of the vast majority of the universe's extent. We are trapped inside our observable bubble, not by physical walls, but by the finite speed of light and the finite age of the universe. The rest of the universe, almost all of it, is dark to us in the most absolute sense. Not dark like the dark of night, which is merely an absence of nearby light sources, but dark like an event horizon. Dark like a boundary beyond which information cannot pass. The universe is not just mostly empty of matter. It is mostly dark in the sense of being forever inaccessible to observation. There is a further subtlety that deepens this picture. As the universe continues to expand under the influence of dark energy, the observable universe is actually shrinking in terms of what we can ever communicate with. Galaxies that are currently within our observable sphere, galaxies from which we are receiving light right now, are, if they are far enough away, already beyond our cosmological event horizon. Their light is reaching us now because it was emitted long ago when they were closer. But any signal we send today will never reach them. The expansion of the universe is already carrying them away faster than the signal could travel. The observable universe and the reachable universe are different things, and the reachable universe is considerably smaller. In terms of what we can ever interact with, ever send a signal to and receive a reply, the horizon is significantly closer than the edge of the observable sphere. The universe is getting lonelier in real time, horizon by horizon, galaxy by galaxy receding, beyond the point of permanent contact. Chapter 9: The Physics of Nothing. What empty space actually is. We keep using the word empty to describe the cosmic voids, the intergalactic medium, the spaces between stars and galaxies. But what does it mean physically for space to be empty? Is it possible for space to be truly, completely, absolutely empty? The answer from quantum field theory is remarkable, deeply counterintuitive, and directly relevant to why the universe is structured the way it is. In classical physics, the physics of Newton and Maxwell, empty space is a straightforward concept. It is the absence of matter and radiation, a region where there are no particles, no fields, no energy, no anything. Classical empty space is perfectly inert. It is a stage on which things happen, but it is not itself a thing that does anything. Quantum field theory, which is our deepest description of matter and energy, says something very different. In quantum field theory, the fundamental constituents of reality are not particles, but fields, quantum fields that permeate all of space. The electron field, the photon field, the quark fields, the Higgs field, these fields exist everywhere, including in regions of space that contain no particles. And quantum mechanics imposes a constraint on these fields that has enormous physical consequences. The fields cannot be perfectly calm. Even in their lowest energy state, the vacuum state, they must fluctuate. The uncertainty principle forbids a field from having both a definite value and a definite rate of change simultaneously, which means the field cannot sit perfectly still. It must constantly fluctuate around its mean value, producing what physicists call vacuum fluctuations, or zero-point fluctuations. These fluctuations are not a theoretical abstraction. They are measurable. The Casimir effect, a force between two uncharged parallel metal plates placed very close together in vacuum, is a direct consequence of vacuum fluctuations. Between the plates, only certain wavelengths of vacuum fluctuations fit, those whose wavelength is an integer multiple of the plate separation. Outside the plates, all wavelengths exist. The result is a pressure imbalance, more vacuum fluctuation energy outside the plates than inside, pushing the plates together. The Casimir force has been measured to high precision. Uncharged metal plates in a vacuum attract each other because the vacuum between them is different from the vacuum outside them. The vacuum is not nothing. It is a dynamical, energetic medium. It is worth being precise about what virtual particles actually means, because the term is used freely in popular science but is frequently misunderstood. Virtual particles are not real particles that briefly pop into existence and then annihilate. They are a mathematical tool, a way of accounting for the quantum fluctuations of a field in a perturbative calculation. A more accurate description is that the quantum fields of the vacuum are always fluctuating, and those fluctuations have measurable consequences. And one way to calculate those consequences is to think in terms of virtual particle pairs. But the virtual particles are a calculational device, not a physical object. The fluctuations they represent, however, are entirely real. They produce the Casimir force, the Lamb shift, and the cosmological constant. The vacuum seethes not with tiny particles popping in and out of existence, but with the irreducible quantum noise of fields that can never be completely still. The distinction matters because the naive picture of particle pairs appearing and vanishing can lead to confusion about energy conservation and other physical principles. The correct picture is that the vacuum is in a state of minimum energy, but that minimum energy is not zero, and it is not static. It is a living, fluctuating, dynamical ground state that underlies every cubic centimeter of the universe in the emptiest voids as much as in the densest stellar cores. Vacuum fluctuations also produce another measurable effect, the Lamb shift. In a hydrogen atom, the 2s1/2 and 2p1/2 energy levels are predicted to be degenerate at exactly the same energy by the Dirac equation of relativistic quantum mechanics. But in reality, they are slightly different in energy. The 2s1/2 level is slightly higher than the 2p1/2 level, a difference of about 1058 megahertz. This tiny energy difference, called the Lamb shift, after Willis Lamb, who measured it in 1947, is caused by the interaction of the hydrogen atom's electron with the vacuum fluctuations of the electromagnetic field. The electron is constantly being buffeted by the random quantum fluctuations of the photon field, and this buffeting shifts its energy slightly. The Lamb shift is a direct measurement of the physical reality of vacuum fluctuations. It is one of the most precisely tested predictions in physics, agreeing with theory to better than 1 part in a million. So the vacuum, the emptiest emptiness, is not empty. It is filled with fluctuating quantum fields, constantly producing and annihilating pairs of virtual particles, constantly shifting in energy. The energy density of the vacuum, the 0-point energy, is a real physical quantity. It is this vacuum energy that is thought to be responsible for dark energy, the cosmological constant that is driving the accelerating expansion of the universe. Here is where one of the deepest unsolved problems in physics enters. The quantum field theory calculation of the vacuum energy density, summing up the zero-point energies of all the quantum fields up to some cutoff scale, gives an answer that is enormous. Depending on where you put the cutoff, at what energy scale you stop summing, the predicted vacuum energy density is anywhere from 60 to 120 orders of magnitude larger than the observed value of the cosmological constant. This is the cosmological constant problem. The discrepancy between what quantum field theory predicts for the vacuum energy and what astronomers actually measure. It is widely regarded as the worst discrepancy between theory and observation in the history of physics. There is no generally accepted resolution. Some mechanism must suppress the vacuum energy to near zero, reducing it by a factor of 10 to the power of 60 to 10 to the power of 120, and leave behind the tiny residual that we observe as dark energy. What that mechanism is, nobody knows. It is one of the most important open questions in fundamental physics. The relevance of this to the emptiness of the universe is profound. The vacuum energy, whatever its magnitude, fills every cubic centimeter of space equally, including the deepest cosmic voids. The voids are not just empty of matter. They are filled with vacuum energy, with quantum fluctuations, with the constant churning of virtual particle pairs appearing and annihilating on timescales so short as to be unobservable. The void is seething with activity at the quantum scale, while appearing perfectly, eerily inert at any macroscopic scale. The emptiness is, at its deepest level, a kind of fullness. A fullness of potential, of quantum possibility that produces no observable effect except the tiny cosmological constant that is slowly expanding the universe towards its cold, dark, empty end. There is another property of empty space that is worth examining here, because it connects the quantum nature of the vacuum to the large-scale structure of the universe in a direct and surprising way. Vacuum fluctuations in the inflationary epoch, the same quantum fluctuations that produce the Casimir effect and the Lamb shift in normal circumstances, are the origin of the density fluctuations that seeded the cosmic web. During inflation, the exponential expansion of the universe stretched quantum vacuum fluctuations in the inflaton field to macroscopic scales. Microscopic quantum noise became the seeds of galaxies. The large-scale structure of the universe, the filaments, the voids, the clusters, the entire cosmic web grew from quantum fluctuations in the vacuum of the inflationary epoch. The emptiness of the cosmic voids was, in the beginning, a quantum fluctuation smaller than an atomic nucleus. The matter distribution of the universe traces its origin to the irreducible quantum noise of the vacuum. This means something extraordinary. The cosmic emptiness and the cosmic structure are both expressions of the same quantum mechanical fact. The quantum vacuum fluctuated. Inflation stretched those fluctuations. Gravity amplified them. And 13.8 billion years later, the result is 2 trillion galaxies arranged in a cosmic web, surrounded by vast empty voids, in a universe whose dominant energy component is the vacuum energy itself. The structure of the universe is quantum mechanics made visible at the largest possible scale. Chapter 10: Dark Energy and the Growing Emptiness. The future is void. The universe is getting emptier. This is not a metaphor or a projection. It is a direct physical consequence of the expansion of the universe driven by dark energy. Every second, the distance between unbound objects in the universe increases. The cosmic voids grow larger, the filaments thin. The galaxy clusters grow more isolated, and the process is accelerating. To understand what this means for the long-term future of the cosmic web and the emptiness it contains, it helps to track what is happening at different scales simultaneously. At the smallest scale, within gravitationally bound systems, the expansion of the universe has no direct effect. The Milky Way is not expanding. The local group is not expanding. The Virgo supercluster is not expanding significantly. Gravitationally bound systems are held together by the mutual gravity of their constituent matter, which is strong enough at these scales to resist the cosmic expansion. Objects within a gravitationally bound system orbit each other, merge with each other, and evolve under their mutual gravity without being pulled apart by the expansion of space. The Earth is not receding from the Sun. The Sun is not receding from the galaxy's center. These scales are immune to the Hubble flow. But at larger scales, scales where gravity is not strong enough to bind structures together, the expansion dominates. Any two galaxy clusters that are not gravitationally bound to each other are being carried apart by the cosmic expansion at a rate proportional to the distance between them, the Hubble law. The farther apart they are, the faster they are receding. Clusters beyond the local supercluster, which itself has uncertain membership and may or may not be gravitationally bound in its entirety, are all receding, carried by the expansion of space. Dark energy accelerates this process. Without dark energy, the universe would be expanding but decelerating. The mutual gravity of all the matter in the universe would be gradually slowing the expansion, and the universe might eventually stop expanding and recollapse. With dark energy, the expansion is not slowing, it is speeding up. The clusters that are receding from us today are receding faster tomorrow. The cosmic web is not merely frozen in its current configuration, it is actively being pulled apart at the largest scales. Over the next few tens of billions of years, the observable universe will increasingly consist of just the local group, the Milky Way, Andromeda, and the roughly 50 smaller galaxies gravitationally bound to them, surrounded by an expanding void. The galaxies of the Virgo cluster, currently about 65 million light-years away, are already near the edge of what will eventually be accessible. In a few tens of billions of years, the accelerating expansion will carry them beyond the cosmological event horizon. The distance, at which recession, velocity equals the speed of light. Any signal we send today will eventually fail to reach objects beyond that horizon. Objects beyond it are already, in a causal sense, beyond our reach. They are just still close enough to be visible. The ultimate fate of the observable universe is what cosmologists call the island universe scenario. In this scenario, the local group possibly merged into a single large elliptical galaxy, Milkomeda, the product of the eventual collision and merger of the Milky Way and Andromeda galaxies, is the only structure within reach. Everything else has receded beyond the event horizon. The night sky will contain the stars of Milkomeda and nothing beyond. No other galaxies, no Virgo cluster, no distant smudges of light from the great wall of galaxies that Hubble first photographed. The universe, from inside the local group will look entirely, perfectly empty beyond the local stars. This is not speculation. It is the straightforward extrapolation of the current cosmological model with a cosmological constant. The timescale for distant galaxies to fade beyond detectability is roughly 100 billion to 1 trillion years, long compared to the current age of the universe, but finite and inevitable given the current dark energy density. An astronomer living 1 trillion years from now in the local group would have no observational evidence that the universe contains anything beyond their local galaxy. The CMB would have redshifted to wavelengths so long as to be undetectable. The distant galaxies would be gone. The cosmic web, which we can currently map with redshift surveys, would be completely invisible. Its existence inferred, if at all, only from theoretical arguments about what must lie beyond the horizon. This has a haunting implication for the nature of scientific knowledge. If the universe had been just a few billion years older when intelligent life evolved, if our civilization had emerged, not now, at 13.8 billion years after the Big Bang, but in 1 trillion years, the evidence for the Big Bang, for the expansion of the universe, for the existence of galaxies beyond our own would not be available. The CMB would be gone. The redshift of distant galaxies would be undetectable. The very knowledge that the universe had a beginning, that it is expanding, that it contains hundreds of billions of galaxies, all of this would be inaccessible. An astronomer in that distant future, looking at a dark, empty sky beyond their local stars, might conclude that the universe consists of a single galaxy, static and eternal. They would be wrong, but there would be no way to know it. We are extraordinarily fortunate to exist at a time in cosmic history when the evidence for the universe's origin and structure is still visible. The window for this knowledge is finite, and we are inside it. The growing emptiness also has implications for the ultimate fate of the matter that now forms, the cosmic web's structure. As the universe expands and the voids grow, the matter in the filaments and walls of the cosmic web continues to drain toward the nodes, the galaxy clusters. Over timescales of tens to hundreds of billions of years, the filaments will thin and eventually dissolve as their matter is consumed by the clusters at the nodes or dispersed by the expansion. The galaxy clusters themselves will continue to grow as they accrete the last of the infalling matter, building increasingly massive, increasingly isolated structures. Eventually, each cluster will exhaust its supply of infalling gas and enter a phase of pure gravitational consolidation. Galaxies within the cluster, merging, their gas consumed or expelled, their stars aging and dying. The cluster will become a vast, dark, cooling system, still bound by gravity, still orbiting around a common center, but growing darker and colder as the stellar populations age. The matter that does not fall into clusters, the gas in the filaments, the stars ejected from galaxies by gravitational interactions, the dark matter halos of the smallest galaxies, will be dispersed into the growing voids. Over cosmological timescales, the voids will become even more tenuous, populated by this dispersed matter at densities even lower than they have today. The cosmic web's current structure, which already sees 70 to 80% of the volume in near-empty voids, will evolve toward a state of even greater emptiness. The matter of the universe will become increasingly concentrated in ever more isolated islands of bound structure, while the volume between those islands grows without limit. The emptiness is not just the current state of the universe, it is the direction of travel. The universe is asymptotically approaching a state of maximum emptiness, and dark energy is the engine driving it there. Chapter 11. Measuring the Void. How we know what we know about the large-scale structure. Everything have described in this video: the cosmic web, the supervoids, the statistics of void sizes, the distribution of galaxies along filaments, comes from observations. It is worth pausing to appreciate how we actually know these things, because the methods are both ingenious and revealing of just how hard it is to map the three-dimensional universe. The most fundamental observational tool for mapping the large-scale structure is the galaxy redshift survey. When a galaxy's spectrum, the distribution of its light across wavelengths, is measured, the spectral lines of known atomic species, hydrogen, oxygen, calcium, are shifted toward the red end of the spectrum by an amount proportional to the galaxy's recession velocity. By measuring this redshift, we can determine the galaxy's recession velocity, and from the recession velocity, using the Hubble law, we can infer its distance. By measuring the redshifts of millions of galaxies at positions across the sky, we can reconstruct the three-dimensional distribution of galaxies in our cosmic neighborhood. The first large-scale redshift surveys were conducted in the 1970s and 1980s, and they immediately revealed the cosmic web. The CFA Redshift Survey, led by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, produced the first maps of the large-scale structure that clearly showed the network of filaments and voids. The famous Stickman image from the CFA survey, a slice through the galaxy distribution that shows a recognizable human figure at the center of a map dominated by voids and bounded by dense walls, became one of the iconic images of cosmology in the 1980s. It was the first time the cosmic web was made visually unmistakable. The Sloan's Digital Sky Survey, which began operations in 2000 and has undergone multiple phases since, is the most comprehensive galaxy redshift survey ever completed. The SDSS has measured spectra and redshifts for approximately 3 million galaxies and quasars, covering about a third of the sky and extending to distances of several billion light-years. The three-dimensional map it has produced of the universe within a few billion light-years of Earth is breathtaking in its detail. A rich, intricate network of filaments, walls, clusters, and voids that matches in extraordinary quantitative detail the predictions of the cold, dark matter cosmological model. The SDSS data has been used to measure the statistical properties of voids with high precision. The void size function, the distribution of void sizes as a function of radius, is a powerful cosmological probe. It depends on the growth rate of structure, which depends on the amount of dark matter, and on the expansion history of the universe, which depends on dark energy. By measuring how the void size function evolves with redshift, comparing the void statistics at different cosmic epochs, cosmologists can constrain models of dark energy and modified gravity. More recent surveys have extended the map to greater distances and higher precision. The Dark Energy Survey, DES, which operated from 2013 to 2019 in Chile and covered 5,000 square degrees of the southern sky, imaged approximately 300 million galaxies in photometric imaging, providing positions but not precise distances. Photometric redshifts are less precise than spectroscopic redshifts, but they can be obtained much faster for large samples. The DES produced one of the most precise measurements of the matter power spectrum, the statistical description of how density fluctuations are distributed across scales, confirming the standard cosmological model to high precision. The upcoming flagship survey instruments will push these measurements to new extremes. The Euclid satellite, launched by the European Space Agency in 2023, is conducting a spectroscopic survey of approximately 30 million galaxies and photometric survey of billions of galaxies, covering the sky over a period of 6 years. Euclid's primary scientific goals are to measure dark energy and the growth rate of structure through 2 complementary probes. Weak gravitational lensing, the distortion of the shapes of background galaxies by the mass distribution of the large-scale structure, and baryon acoustic oscillations, the imprint of sound waves from the early universe on the galaxy distribution, which provides a standard ruler for measuring the expansion history. The Dark Energy Spectroscopic Instrument, DESI, operating at the Kitt Peak National Observatory in Arizona, is conducting the most extensive spectroscopic survey ever attempted, targeting 40 million galaxies over 5 years to map the 3-dimensional cosmic web with unprecedented precision. What these surveys ultimately measure, beneath all the technical complexity, is the shape and evolution of the emptiness. Every void mapped, every filament traced, every cluster cataloged is a data point in the reconstruction of the cosmic web. The voids, far from being scientifically boring regions of nothing, are among the most powerful cosmological tools available. Their shapes are sensitive to modifications of gravity. Theories in which gravity behaves differently from general relativity predict slightly different void shapes. Their sizes are sensitive to dark energy. Their internal dynamics, the small-scale flows of matter within and around them, are sensitive to the total matter density and the neutrino mass. The emptiness, it turns out, is one of the most information-rich environments in the observable universe. There is also a technique called the Alcock-Paczynski test, which uses the statistical isotropy of voids to constrain the expansion history of the universe. In a universe undergoing isotropic expansion, the average shape of a void, when its 3-dimensional structure is reconstructed from redshift data, should be spherical. Any systematic elongation or compression of the void shapes in the redshift direction compared to the transverse direction indicates a mismatch between the assumed and actual expansion history. This test is one of the few techniques that can measure the ratio of the expansion rate at different epochs independently of any assumed model of dark energy, making it a powerful complement to other cosmological probes. The voids are, in effect, cosmic precision instruments. Chapter 12: The Emptiness and the Constants of Nature. Why the universe is the way it is. The universe is empty in the specific way it is empty for reasons that trace back to the fundamental constants of nature and the initial conditions of the Big Bang. This is not a trivial observation. A universe with slightly different constants would be empty in a very different way, or might not be able to form complex structures at all. Consider what happens if you change the strength of gravity. Gravity is the force that drives structure formation. It amplifies density fluctuations, collapses gas into stars, binds galaxies into clusters, and builds the cosmic web. If gravity were significantly stronger, structure formation would proceed more rapidly and at smaller scales. The universe would form structures more quickly, but they might be too dense and short-lived for complex chemistry and long-lived stars. The first stars in a stronger gravity universe would be more massive, burning faster and producing supernovae on shorter timescales, seeding the universe with heavy elements, but potentially disrupting the gas in young galaxies before planets could form. If gravity were significantly weaker, density fluctuations would grow more slowly, and the universe might remain smooth and featureless. A nearly uniform sea of gas, for far longer than its current age, never forming the galaxies and stars in which heavy elements are synthesized and planets are assembled. The specific strength of gravity in our universe, combined with the specific amplitude of the primordial density fluctuations, which is determined by the energy scale of inflation, produces a universe in which structures formed at the right time and the right size to allow stars with billion-year lifetimes, planetary systems, and eventually biology. This is a constraint, not a coincidence. Anthropic reasoning tells us that we should not be surprised to find ourselves in a universe capable of supporting observers, but it does not tell us why the constants are what they are. Now consider the cosmological constant, dark energy. The observed value of the cosmological constant is extraordinarily small by the standards of quantum field theory, as we discussed in the previous chapter. But it is not zero, and this specific non-zero value has a profound effect on the cosmic web and the emptiness of the universe. If the cosmological constant were much larger, even by a factor of 100, the accelerating expansion of the universe would have begun much earlier in cosmic history, before the matter distribution had time to develop the filamentary structure of the cosmic web. Structure formation would have been truncated. Galaxies would have begun to form, but the accelerating expansion would have diluted the gas too rapidly for much of the filament and cluster structure to develop. The cosmic web would be far less developed. Galaxies would be less massive, and the universe might not have the right conditions for long-lived solar-type stars and planetary systems. An astronomer in a universe with a cosmological constant 100 times larger than ours would see a sparser, younger-looking universe with smaller, more isolated galaxies and less developed large-scale structure. If the cosmological constant were slightly negative, corresponding to a universe that will eventually recollapse, the long-term fate of the cosmic web would be very different. The voids would eventually stop growing, the expansion would eventually halt and reverse, and the cosmic web would begin to contract. On the way to the big crunch, the voids would fill back in as matter falls inward, the filaments would thicken, and the clusters would merge. The universe would grow increasingly dense and hot. The emptiness would be temporary in a way that it is not in our actual universe. The fact that we live in a universe with a small but positive cosmological constant, producing a universe that will expand forever, with voids that grow without bound, is at minimum consistent with the conditions needed for complex observers to exist. A universe that recollapsed before complex chemistry could develop, or a universe that expanded too fast for galaxies to form would not produce the kind of observers who ask questions about cosmic emptiness. The specific emptiness we observe, the cosmic web in its current state, at this particular epoch, is one of the conditions of our existence. The specific amplitude of the primordial density fluctuations is equally important. The fluctuations that seeded the cosmic web have an amplitude of roughly 1 part in 100,000. This amplitude, encoded in the CMB as temperature variations of about 30 microkelvins, is just large enough to allow structure formation on the timescales available in a 13.8 billion-year-old universe, and just small enough that the resulting structures are not immediately and uniformly overdense. If the amplitude were 10 times larger, the early universe would have formed dense structures much more rapidly, producing a universe dominated by massive black holes and extreme radiation environments rather than stable, long-lived stars. If the amplitude were 10 times smaller, structure formation would be much further behind schedule. The universe would still be largely smooth, with only the earliest stages of galaxy formation underway. The 1 in 100,000 amplitude we observe is, in some sense, the Goldilocks amplitude. Not so large, that structure formation was violent and chaotic. Not so small, that structure formation has barely begun. It produced a universe in which, at 13.8 billion years, there are complex, long-lived stars, planets, chemical evolution, and observers. And it produced the specific texture of the cosmic web, voids of tens to hundreds of millions of light years, filaments of comparable length and modest thickness, clusters of thousands to tens of thousands of galaxies at the nodes that we observe in our surveys. The emptiness of the universe is not arbitrary. It is the specific emptiness permitted by the constants of nature and the initial conditions of our particular Big Bang. And that specificity is, in the eyes of many physicists, one of the most important clues about the deeper structure of physical law, about why the constants are what they are, whether they are fixed by some underlying theory or vary across an ensemble of universes, and what the universe would look like if they were different. The void is not just an empty stage. It is a measurement of the universe's fundamental parameters, written in the largest possible handwriting. Chapter 13: The Emotional Weight of the Void. Why the emptiness matters. There is a reason this video is titled, Why the Universe is So Empty, and it's scary. The emptiness of the universe is not just a scientific fact, it is an existential one. And the history of human thought about cosmic scale suggests that the emotional response to the true emptiness of the universe is not something to dismiss as irrational. It is a natural and, in some sense, appropriate response to one of the most fundamental truths about reality. Blaise Pascal, the 17th century French mathematician and philosopher, wrote in his Pensées, Le silence éternel de ces espaces infinis m'effraie. The eternal silence of these infinite spaces frightens me. Pascal wrote this before the telescope had revealed the full extent of the cosmos, before galaxies had been discovered, before anyone knew that the universe extended beyond the Milky Way. He was responding to the Copernican revolution, to the revelation that the Earth is not the center of the cosmos, that it orbits the sun, that the stars are distant suns at inconceivable remove. and even that limited revelation was enough to produce what we might recognize as the correct emotional response, a kind of vertigo in the face of scale. The scale Pascal was responding to was nothing. He was frightened by interstellar distances that we now know are a tiny fraction of the distances to the nearest galaxy, which are themselves a tiny fraction of the distances to the edge of the observable universe. He did not know about the cosmic web. He did not know that galaxies are separated by millions of light years of intergalactic void. He did not know that the observable universe contains 2 trillion galaxies whose total matter content averages out to 6 atoms per cubic meter. If he had known all of this, the word frightened might have been inadequate. What is it about the emptiness that produces this response? Part of it is clearly the question of significance, the worry that in a universe so vast and so empty, any particular arrangement of matter on any particular planet is cosmically irrelevant, drowned in a sea of indifferent void. This is a response to scale in the sense of relative size. We are very small compared to the universe, but this reading misunderstands what the emptiness actually implies. The universe being mostly empty does not make the things that exist within it less real or less significant. A rare configuration of matter, a planet with liquid water, and replicating chemistry and eventually consciousness, is not made less valuable by the vastness of the surrounding void. The void is the context, not the content. There is a version of this argument that is worth taking seriously on its own terms, however. Rarity in the physical sense, the sense in which life occupies a tiny fraction of the universe's volume, is genuinely remarkable, regardless of its philosophical implications for meaning. Consider that a single human brain contains approximately 86 billion neurons connected by roughly 100 trillion synapses, forming a network of extraordinary complexity that processes information, maintains a model of the world, generates intentions and emotions, and is, in some sense we do not yet fully understand, the substrate of experience. Now consider that this brain is assembled from atoms that are, in the cosmic average, separated by meters of empty space. The atoms themselves are mostly empty. An atom is 99.9999999999996% void, with its electrons occupying a cloud of quantum probability around a nucleus that, if the atom were the size of a football stadium, would be the size of a fly at the center. The brain is a structure of enormous complexity, built from things that are themselves almost entirely nothing, embedded in a universe that is almost entirely nothing. The fact that this is possible, that complexity and consciousness emerge from a universe so thoroughly dominated by void, is one of the deepest puzzles in science and philosophy simultaneously. But there is a deeper source of unease that is harder to dismiss. It is not the smallness of humanity relative to the universe. It is the specific character of the emptiness. The fact that it is not random, not uniform, but structured and shaped by physics that we understand well enough to predict, but not well enough to fully explain. The cosmic web is built from dark matter that we cannot see, and dark energy that we cannot explain, seeded by inflation that we have never directly observed, shaped by a cosmological constant that quantum field theory predicts should be 120 orders of magnitude larger than it is. The emptiness we observe is not the emptiness of a well-understood cosmos. It It is the emptiness of a cosmos that we have mapped precisely, but understood only partially. We know the shape of the void. We do not fully know what fills it, what built it, or why it is the specific void it is, rather than some other possible void. This is the frontier of science, the place where precise measurement meets incomplete understanding. The cosmic web is one of the most precisely characterized structures in all of science. Its statistical properties, its evolution, its connection to the CMB, its dependence on cosmological parameters. All of these are known to extraordinary precision. And yet, the dominant components of the universe that built the web, dark matter and dark energy, remain fundamentally unknown at the level of particle physics. We have mapped the architecture of the universe without knowing the nature of the building materials. There is also the question of life. If the universe is structured the way it is, mostly empty, matter concentrated in rare islands of structure separated by growing voids, what does that imply for the distribution of life? The cosmic web concentrates matter in galaxies, and galaxies are where stars and planets form. Life, as far as we know, requires stars and planets. So life is concentrated in the dense nodes and filaments of the cosmic web, not in the voids. But within those nodes and filaments, the actual density of life-bearing planets relative to the total volume is still vanishingly small. Even if every solar-type star in every galaxy had an Earth-like planet with life, the fraction of the universe's total volume occupied by living things would be negligible to the point of unmeasurability. We exist in a universe that is almost entirely devoid of anything resembling what we value. Consciousness, complexity, life, these are extraordinarily rare against the background of the cosmos. The universe produced them, but it produced them in a tiny fraction of its volume, on a subset of planets, orbiting a subset of stars, in a subset of galaxies, in a subset of the cosmic web's nodes. And we have no idea whether it produced them elsewhere, or whether we are alone. A single data point of complexity in a sea of indifferent void. This is not a reason for despair, but it is a reason for the kind of vertigo that Pascal felt, scaled up by every order of magnitude that modern cosmology has added to the picture since his time. The universe is not designed around us. It is not structured for our benefit or our comprehension. It is a specific physical history that produced, as a byproduct of its physics, the conditions for our existence in one small corner of one small galaxy in one arm of the cosmic web. And the cosmic web, the largest structure we can observe, the framework of the entire universe, is mostly empty space, mostly void, mostly nothing. That is the correct thing to feel some awe about, not because it diminishes us, but because it is genuinely, astonishingly strange. Conclusion: so this is what the emptiness of the universe actually is. It is 6 hydrogen atoms per cubic meter, on average, across the entire observable universe. It is 70 to 80% of the universe's volume in cosmic voids, near empty spherical regions, tens to hundreds of millions of light years across, where matter has flowed away under gravity and left behind a near-perfect void. It is 2 trillion galaxies concentrated in the thin filaments and walls of the cosmic web, a structure that looks like foam or neurons, or the branching of a lung when visualized at its full scale. It is dark matter that we cannot see, providing the gravitational scaffolding that the galaxies trace. It is dark energy that we cannot explain, accelerating the expansion of space and growing the voids without limit, carrying galaxies beyond the cosmological event horizon, one by one until eventually, only the local group remains visible. The emptiness is not a default, not an absence of something that should be there. It is the active, dynamic result of 13.8 billion years of physics. Inflation producing the seeds, dark matter building the structure, gravity amplifying the variations, dark energy stretching the result into the cosmic web we observe. Every void in the universe is a region where matter once was, or might have been, and chose, under the logic of gravity, to be somewhere else. The voids grew because matter fell toward the overdensities. The overdensities grew because matter fell from the voids. The universe sorted itself into structure and emptiness as an inevitable consequence of its own initial conditions and its own physical laws. The emptiness is also a message. The specific way the universe is empty, the sizes of the voids, the statistics of the cosmic web, the amplitude of the density fluctuations that seeded it, encodes the fundamental parameters of cosmology. Dark energy, dark matter, the neutrino mass, the spectral index of the primordial fluctuations, all of these are imprinted in the texture of the cosmic web. When astronomers map the voids and filaments with redshift surveys, they are not just making maps. They are measuring the universe's deepest properties, written in the geometry of the emptiness. And the emptiness is growing. The voids are expanding. The galaxies beyond the local group are receding. In 1 trillion years, the sky will be dark beyond our local stars, and any future observer, if there is one, will have no evidence that the universe contains anything beyond their own small corner of it. The window of cosmic knowledge is finite. We exist inside it right now. The evidence that the universe is vast, that it had a beginning, that it is mostly empty and expanding toward maximum emptiness. All of this is currently visible, currently measurable, currently knowable. And the fact that we know it, that we have built instruments sensitive enough to detect the whisper of 6 atoms per cubic meter across billions of light years, is not a small thing. It is one of the most remarkable facts about this brief, warm, improbable arrangement of matter that we call a civilization. The universe is almost entirely empty, and we somehow are here inside it, asking why.